The Traveling Salesman Problem. Narrated by Athena Herman, researched by Leslie Marks, and edited by Stuart Kinzelman. Some of you may know the Traveling Salesman Problem as the Traveling Purchaser Problem and the Vehicle Routing Problem. These all have the same premise. No matter what name you're using, basically, you're trying to figure out, given a list of cities and the distances between them, what is the shortest possible route that visits each city exactly once and returns to the city of origin. The traveling salesman problem is considered an NP hard problem. So what does that actually mean? NP stands for a hard, non-deterministic polynomial problem. Still not getting it? Think of it as a problem that is so hard it takes your computer a long time to figure out. Let's take a moment to walk through some of the history of TSP. The official problem that you heard just moments ago was created in 1930. But people have been thinking about this problem long before then. In the 1800s, an Irish mathematician, W.R. Hamilton, and a British mathematician, Thomas Kirkman, created the first mathematical version of this problem. 130 years later, you really begin to see this problem being worked on in both Vienna and Harvard. However, the problem really didn't start taking off until the 1950s and 1960s, where the popularity grew so great that the RAND Corporation offered a cash prize to anyone who could make any sort of headway on the problem. The first 3 people to get any sort of payouts were named George, Delbert, and Selmer. All 3 of these individuals happened to be workers at the RAND Corporation, and they discovered that really this is an integer linear program that can be run on a computer. These 3 gentlemen used what they deemed the cutting plane method to solve their problem and earn their payout. This method is very complicated, and so we're going to start off by showing you some simpler ways to solve this problem. There are really 4 good, we'll use that term loosely, ways to solve TSP. To explain these methods, we will be using landmarks from the Boise State University campus. The Business Building, the Morrison Center, the Boise State Bee, the library, the Student Union Building, and the Blue. The first method you can use is randomly choosing where you go from building to building, starting at the Student Union Building and returning there. As you can tell, with only 2 iterations, there are many more ways you can do this, and so it would take a lot of time to find the solution. The next method is called the SA temperature method, which basically is a way to organize the randomized method. You start with a randomized pathway, and then, depending on its length, you assign it a temperature. A hot temperature means it's long, a room temperature means it's medium, and a cold temperature means it's short. In this case, since it is a longer pathway, it is considered hot. You then continue to make different pathways and compare them based on their temperature. Your coldest one is your shortest one and the one you should keep. Whenever you get a pathway that is shorter than any of the others, you keep it and use it as your comparison. If you are following the examples, you will see that I made a room temperature pathway, and that is now our new comparison. The last iteration I make in this example is a cold or short pathway. This is our winner. To explain again, if the iteration is colder, then it's the new comparison. If it's hotter, you basically throw it out. The coldest temperature you find is also the shortest distance and your winner. The next method we're going to talk about is called the greedy method, and it says you always choose the next closest landmark. In our example, when you start at the Student Union Building, you go to the library, then the Boise State B, then the Morrison Center, then the business building, then the blue, and then back to the student union building. But are we sure this is the best method? The answer to that question leads us to the next method, the two-op tour. What the two-op tour does is basically uncross sections of the pathway. Seeing in this rectangle here, there's a cross in the center. Using the two-op tour, you uncross it and make it a complete rectangle. Looking at our original pathway from the greedy method, you see this. See how there are crosses within that method? Using the two-op tour, we take out a couple of those crosses. There's still one left though. Sometimes you have to make multiple two-op tours to find the ultimate answer. Our last example shows a completely uncrossed two-op tour and our winner. This has been our brief introduction into the traveling salesman problem. Thank you for watching.